Congratulations, you're taking Calculus 3. So Calculus 3 is multivariable calculus. What that means is we're either going to be looking at functions that take more than two variables as inputs, or possibly functions that take more than two variables as outputs. That is the multivariable aspect. Instead of just one input and one output, we can have multiple inputs or multiple outputs. Great. Now in single variable calculus, we have an input and an output. We just need two variables and we can deal with the coordinate plane when we use geometry to visualize what's going on. With multivariable calculus, we're going to have at least three variables floating around. One input, one output, and at least one more of one or the other. So that means that we have to deal with at least three dimensions when dealing with geometry. Now, I don't know about you, but I don't really have a good intuitive way about thinking of geometry in four or more dimensions. I don't understand what four spatial dimensions really means. I can't visualize it, I can't draw it, so that's a bummer. We're not going to be able to do a really good geometric visualization of four or more variables. But with three variables, we are dealing with three dimensions, and we live in a three-dimensional world. So you have a decent intuitive understanding of three-dimensional space. So three-dimensional space is a fine place for us to visualize at least the simplest case of multivariable calculus, which is either two inputs or two or even three outputs. However, when we're drawing things, we are going to have to, we're dealing with two-dimensional surfaces. This paper is two-dimensional, your screen is two-dimensional, etc. But that's okay because you also have a lot of experience in seeing three dimensions represented on two-dimensional surfaces. You watch videos, you see pictures, you take pictures, you see drawings and paintings, etc. You are familiar with inherently your vision is kind of two-dimensional. So you are familiar with looking at a three-dimensional space and interpreting it through the lens of a two-dimensional surface, a two-dimensional representation system. So we're going to learn how to draw nice mathematical pictures of three-dimensional space on two-dimensional surfaces. So here we go. Three-dimensional space requires three coordinate axes, just like two-dimensional planes require the coordinates x and y. We need x, y, and z, and I've decided upon the convention for whatever reason that x is red, y is green, and z is blue. Now recall with the plane, when we write down the x and y axes, they intersect in a line called the origin, or a point called the origin, and we're going to have the same thing here in three-dimensional space. And we also choose a positive direction. X, we choose to be a horizontal axis, and we choose right to be the positive direction. Y is a vertical axis, and we choose up to be the positive direction naturally. However, when we deal with x, y, and z, we have to choose two of them to be, say, a good choice is for two of them to be horizontal. We're going to let x and y be horizontal axes. They lie in a plane, horizontal plane. Then z is a vertical axis. And we have to have some way of choosing what the positive x, y, and z directions are. So really, you could arbitrarily choose x and y to have positive directions, and then z will be uniquely determined by your choice of x and y. And this is called the right-hand rule. But in fact, let me sort of describe the right-hand rule as a way of determining the directions, the positive directions for all three axes. So what we're going to do is take your right hand. Here's a drawing of a right hand, and you stick out your finger. You're like, hey, check that out. Look over there. You're cool. Boo, boo. Okay. And my pointed out index finger is going to be my x direction, my positive x direction. To choose my positive y, I'm going to see which way my fingers curl around. I can't bend them backward. I would break my fingers. They only go naturally this way. So shown by this green arrow, that is bending around to the positive y direction. So the positive y direction is determined by the way that I can turn my fingers. Finally, once I see which way is positive for x and positive for y, my thumb pointing up into the air tells me which way is positive for z. So I think what could be a good question is, think about why the left-hand rule would give you a different positive direction for z. Okay, so each pair of axes determines something called a coordinate plane. So normally when dealing with the xy plane, we have an x-axis, the y-axis, and all the points kind of spanned by those two axes form a plane. So right here we see the typical old xy plane, but now it's a horizontal plane sort of coming out from us and going off into infinity forever. Then we have a plane that is between these two lines for x and z, these two axes. That's the xz plane. And then we have the yz plane, which is the plane that contains the lines, the y-axis and the z-axis. Now, if you're having a little bit of trouble really understanding what this picture is supposed to be, imagine that you're in a room. I mean, right now you're probably in a room, and look at one of the corners. Let that be your origin. Then the x-axis is where the floor meets the wall to the left. The y-axis is where the floor meets the wall to the right. The z-axis is where the two walls meet. The xy plane is the floor. The xz plane is the wall to the left. The xy plane is the wall to the right. So that's really what we're picturing. If you ever really need help thinking about what exactly these axes look like, what exactly space looks like, what exactly coordinate planes look like, think about the corner of a room. So we're setting all this up so that we can identify points using coordinates. And since we've got 3 dimensions, we have to identify points by ordered triples of real numbers. There's an x coordinate, a y coordinate, and a z coordinate in that order. The order matters because the first one tells you how far you go in the x direction, the second in the y direction, the third in the z direction. If you move the numbers around, you might get a different point. So to plot the point with coordinates a, b, c, we start at the origin and we move a along the x-axis. This is really sort of moving a away from the yz plane. Then we move b in the direction of the y-axis. So we're really moving a distance of b away from this xz plane, b. Finally, we move up c in the direction of the z-axis. So we're moving away from the xy plane now and shooting up here. So this point is supposed to be a along the x-axis, b along the y-axis, and c along the z-axis. If we assume a, b, and c are positive, which it looks like they are here, then what that suggests to us is that this point is actually inside of the room, determined by the 3 coordinate planes, at least the side of the room facing us. We call this the first octant. The axes cut up space into 8 octants. We don't have names for all of them, at least I suppose you can number them, but I don't think there's really a canonical or typical or usual numbering of them. But at the very least, where all of the coordinates are positive is an important place for us. That is the first octant, and that's like the inside of this room that's determined by the floor, the xy plane, and the 2 walls being the xz and yz plane.